Hello everyone, hello Group A, you are Group A. Welcome to this course. Hello Group B and C. Do you receive us? Great. So welcome to this course on TCP-IP. Under the conditions that prevail this semester, we'll try our best. I'll start with the first introduction of organization material. Where do I need? I think I've lost the control. Yes. Let me introduce the group of TAs who will be helping. Because of the restrictions, they are not in the room today, except Aladdin. Aladdin is our head TA and is responsible for the Moodle site and for the organization of the exercise in general. And we have this nice group of 4 other people who will be helping us with the lab. And you will meet them in person or via Zoom tomorrow in the lab. This course is at the master level. It's a level setting course, so the goal is to give you a fundamental understanding of all the basic elements that the protocols and the way things are organized in the internet and in networks that use the same technologies as the internet. It's a practical course, primarily, but there is also some theory behind. It's not a theory like you can have as a signal processing course, for example. The theory is much more shallow, but still it is a good way to better understand what happens if we understand what lies behind the things. But the practical part is very important, so expect to spend some time on the labs. There are 4 hours of practical exercises every week, which are not meant to be exactly the time at which to work. We'll talk about that in a second. The work can be done very much in your own time and as you feel better from your organization viewpoint. When we teach such a course, there are 2 contradictory requirements. The first one is, well, if you look at all the details of how TCP, IP, and QUIC, and all the zillions of things that have been invented since then are organized today, there are many, many details. So I'm sure many of you have already dived into doing things with the computer, with organizing some things that has to do with the network, with HTTP or whatever, and then it's an avalanche of details. So that's the first thing. And of course, there's a technique viewpoint. If we want to be efficient at deploying some techniques, we must master those details. So that would be one possible goal, but we will not be able to do that in this course. We will need a full-time semester to be able to do that. So you will not be operational if you go tomorrow to Swisscom and you have to set up their 5G station for MPLS, for example. You should expect to have some training time to understand how you do it completely with all the details. So an opposite viewpoint is to say, let's do a pure theory part where we teach only the nice, probably mathematical parts of the course, but that would probably not help you if you go to Swisscom next semester for practical work. So what we'll do instead is a mitigation of those 2, a mixture of these, which is called by some people who teach this course the rake philosophy. A rake is this instrument that has both breadth and depth. We will cover the breadth, so we will cover all aspects of networking to give you a global image, and we will dive deep into selected topics, primarily those of the labs. So in one lab, you will really set up an OSPF network, which was one of the classical jobs you have to do if you work as a networking engineer in any company. But we will do other things. And the hope is that those selected labs and practicals, and also in the theoretical details, have been chosen in such a way that you have a good coverage of the material. So if tomorrow you go to Swisscom, chances are you will not fall exactly in one of those, except if you go to work for BGP or SPF. If you go to something else, hopefully you will be in between and you will be able to interpolate from what we've learned here. It is important in the context of this course, probably in the context of any course you take at EPFL, to differentiate between why and what versus how. Why and what, when we talk of a technological artifact like a computer network or a smart grid or any device that is man-made, usually this stuff was invented by people like us. So the complexity is probably not that large because it's been invented by people like us. So people like us, with extremely rare exceptions, and you will probably never meet more than one in your entire life, are not able to invent things that are much more complicated than what you and I can do. So the first thing to recognize, so if we don't understand, it's not because there's a mysterious, fantastically complicated and genial thing behind, but it's just that probably we don't know why and what it's doing. So if we ask the question why and something was invented and what it is doing, usually we can fairly well imagine very often how you would do it. Right? If you have to devise an application that does something, a billboard or an add-on to a social network, probably you would have an idea how to build it. Right? If somebody describes to you how it is built, that may be very, very long and not so interesting. Right? So the why and what are usually short. The how may be very complicated. Most often can be guessed, not always. Sometimes when you guess things, it is not exactly how you guessed it, but then that's good, because that means that's the only thing you need to learn. Once you know why something is invented, you imagine in your head how it is done, then you realize how it is really done by reading the doc or looking at trying with the system. If you see a difference, then that's the thing you need to learn. If you see no difference, you don't need to learn it. You've already invented it in your head. So that's a form of compression that we can do. And we need to compress because there's so much stuff. And most of the stuff is relevant only when you know the why and the what. Very often people don't do that. So they will tell you, do this, do that, the long series of technical points. And that gives the appearance of more complexity than there really is. I encourage you to look at Wikipedia for any, probably I don't need even to encourage you. So Wikipedia is an example that, with a few exceptions, but most of the time it will explain you the how in large detail. Sometimes it's a bit frustrating because it will not always give the why and the what. So I encourage you, if you find a Wikipedia article that doesn't give the why and the what, why don't you add it to this Wikipedia article, and then you will do a good service to the community. As I said, this course is a very practical course, so we will have labs every week. There are 7 labs in total, 2 weeks for each lab. The last one lasts only 1 week to avoid spilling over the Christmas vacation. The labs are all mandatory and graded. They can be done entirely in your machine. This is new this year, so there is no penalty if you cannot attend the lab session. So we will use a virtual machine, which means you need a processor that's able to do virtualization. But if you don't have an extremely old machine, that should be okay. And you need some free space on your hard disk, 7 or even a bit more of gigabytes, to put all the routers, all the equipment that we will put virtually in the machines. You can work in pair. In some of the labs, we will ask you to connect 2 computers. But so you need that the 2 who are working in pair are able to work together and connect together. If you can't, then you will be able to skip that. Some labs have a bonus research exercise. This is to address the variety of your backgrounds. Some people are very fluent. The labs will be with Linux and require some Python programming for some part of it. So if you're very familiar with that, perhaps some of the things will look trivial to you. If that's the case, we have prepared for you some bonus research exercises. They're never mandatory, so don't feel obliged to do them. It's more important to do the rest very well, understand the lecture, do the quiz I mentioned a minute ago, I will mention in a minute, and do the mandatory part of the lab. Of course, all info is on Moodle, which we use as the primary source of communication with Zoom. New this year also, there are quizzes every week. So if you go to Moodle, you will see already the quiz for this week and for next week. Those are small questions, very short questions. Some might take a few seconds to answer, some might take a few minutes. And the idea is that you should do them on the fly. You should do them every week. So every week you should do one quiz to challenge you with your understanding of the lab. Something like TCP-IP is made of a huge collection of very simple things. So every single thing that we'll do is simple, most of it, with very rare exceptions. But there is complexity in the addition of all those simple things. So it's important to do it piece by piece. If you do 14 quiz and you follow the 14 lectures and do the 7 labs, it will come without pain, and then you will know quasi everything you need to know about TCP/IP here. The quizzes are chained. You must do quiz 2 before, you must do quiz 1 before doing quiz 2, and you must be up to date with your quiz 1 and 2 before submitting the first lab. For some reason, the labs are numbered starting at 0, and the quiz are numbered at 1. So your work every week is to attend in person or in Zoom or remotely the lecture, which is uploaded on YouTube shortly after the session here. Do the online quiz and advance and complete the labs. And the labs are tomorrow in these rooms, INF1 only, for those of you who are in group B tomorrow, and for the others over Zoom here. You can use the labs to get help, in particular at the beginning, if you block with installing the virtual machine or whatever, then it's very convenient to be in the lab in Zoom or in presence to raise a hand and get some help to be unblocked. But of course, you can also do the lab during the entire week, and the Moodle forum is attended the whole week during business hours. So that's the primary source of communication that we would like to encourage, to post your questions on the Moodle forum. During the course, in person and on Zoom, I use SpeakUp. SpeakUp is a small app that is used for polls. It's not integrated with Zoom because the polls in Zoom are a bit awkward to use. So we will regularly break the flow of the lecture to ask a few questions. Here is the first one. So you should be in this room. The room will be the same during the entire course. So you can, this number should not change. And then I would like to, I pose a question like this one. In which case, in which section are you, essentially? So the idea is to use your own device, give the answer, and when I close the poll, you will be able to see all the answers that have been given. So it's the first year we do it with a large number of people that are both in class and somewhere else. So the performance might be a bit less good, but we'll try. I close this poll in a few seconds. I see on my device the number of votes slowly increasing. So my stopping criterion is when it becomes stationary. Now I close, and you should see the results on your screen. So you see that the huge majority is from computer science, and but also a non-negligible number of people from other sections. And the course has been designed and made to be available for anybody from any section, so that should be okay. SpeakUp allows you, like the chat on Zoom, to post and broadcast messages. You know the rules of EPFL. I don't need to repeat them, but in the past years we had some problems. So please use ethically. Don't insult other people. The stupid stuff you keep it for your Facebook or Instagram account, but not here. The only thing that requires physical presence of everyone will be the final exam. That will be in the exam session in January or February. The exam is closed book and no electronic equipment other than a simple calculator, but there's in principle no calculation to do. So it's closed book. That means that you should know in your head enough things. Of course, we live in the age of Wikipedia and the internet. There is no sense learning by heart, for example, what is the format of an IP packet. So all those tedious details are available in an exam booklet, which is already available on Moodle. There might be minor changes to that, bug fixes or things like this, but it is already on Moodle so that you see this, you see it now, and the exam booklet is what we will give to you during the exam. So if it's in the exam booklet, you don't need to know it by heart. All the rest you do. You do need. Grading is 50% the practice and 50% the exam. And here are the details of the practice. The practice is the average of all labs. Since the last lab is only half a lab, it has a smaller weight. And the research exercise bonus, which is the additional questions that you can have in some of the labs, in practically all of the labs, can be added to your lab grade here. And the final grade is the average of the theory grade and the lab grade, and we never round any grade except the very final one. So those are the grading rules. Voila, that's the end of this organizational part. Are there any questions? In class, I think you can ask, you can speak through your mask if you have questions, or in the chat that I don't see anymore. Do you see your chat?
Yes.
Yes.
So there's one question. There is no validation button, right? But what I don't know. For speaker.
I'm not sure. Are groups mandatory or can we work alone? That's the question about the labs. The groups are mandatory formally in the sense through Moodle, you need to be in a group to upload the lab, but you can be in a group with a single person. So it is possible to work alone if you prefer. It's also possible, and in fact encouraged, to work by group of two because the nature of the work, which has a lot of typing, sometimes is better if you can share the work, but you can always do it alone. Good. Then as soon as I recover my screen here, without further ado, we move on to the first chapter of this class. Which is a high-level view of everything. So we will cover all the aspects that are given in this thing we will see today in more details through the year. But it's impossible to do things in a serial way. If we would do everything we need to know about the IP layer first, then we would not be able to do any lab. So in order to do practical work, we need to have a first global view of everything. So that's the first thing we will do now. It's very short, very shallow, but still we will go through a few fundamental things. That's what I call the architecture. The architecture is formally the set of rules that are dictated by or set up by a body called the Internet Engineering Task Force, which is the standardization body for all the Internet protocols. I use a textbook for the slides are in principle self-contained, except when I will give a few exceptions. If you want to know more, or if you find that you don't understand enough by simply listening or watching the video, I follow very closely this book, which is a book that's freely available online, that is mentioned on the Moodle site. You can get directly the book if you want to get more. The first thing that you probably heard already about TCP-IP is that there are layers. So what are layers? Well, layers are nothing else than what we call modules in software. When we build a complicated piece of software, then a very important thing is how you divide the different modules. And the big projects that fails are the one where the division was not well done. But what is special in networking is that the modules are also that we communicate. So if I do a module, for example, called the application, then it's not a module that is standalone, but it speaks to other modules of the same nature. So modules of the same nature are called layers. Another aspect is that there is a a ranking of the layer, one on top of the other. Depending on the book, sometimes you will read that there are 7 layers. Today, most people would agree that there are 5 layers, and we will discuss in detail what they do. The physical layer is about transporting information about physical phenomenon, wires or wireless waves. The network and MAC layers are about interconnecting systems. Why there are 2, we will discuss a bit later. And the transport and application layer are about what we're interested in to do the communication. So if we go to Facebook, we use the Facebook application layer. And there is also Facebook that is also using another layer, which is called the transport layer. So we'll discuss them in detail. So the application layer is, of course, what we're interested in. And this is, of course, the richest part of communication networking. This is what contains the applications, the distributed system, and the security. All of those topics are the subject of other courses. So we will not cover in detail how you code a complex application, for example. We will also not cover in detail how cryptography works, but we will, of course, mention the security aspects of all the things we're interested in the network. So network and security are, of course, 2 topics that go together. So expect that we will have a few topics of security. So the application layer is Facebook, YouTube, etc., Zoom. Those are application layers. A bit more hidden is the transport layer. The transport layer is also end-to-end. It resides in the hosts, not in the core of the internet, in principle. I said in principle here because, in fact, everything I say is probably wrong if I don't add in principle, because the internet is made of largely software. In software, you can have a design, you can have rules that say you do this and not that. But if you do the forbidden thing and it works, probably, and the world will not collapse. You're not breaking any physical law and not any real law, so it will probably work. So we'll see examples of violations of the architecture. But if I would present to you immediately how things are with all the violations, and it will look like chaos. It is not chaos. The internet is made on a number of rules, some very simple rules, and I will uncover them one by one in the course. But of course, once in a while, people have found shortcuts to avoid the rules, but it's important to recognize them as shortcuts rather than a flat, complete nonsense here. So one of the rules is that the transport layer is end-to-end. When A talks to B, there is a transport layer entity in A and B, but not in all the intermediate things, the routers, the bridges, the DNS servers, etc. They are not involved with this transport layer. The goal of the transport layer is to provide a unified programming interface to application programmers so that they don't need to always redo the same thing. That happens, of course, at zillions of layers. When you write an application program, you use object libraries that also do a number of things, but the low-level things are called the transport layer. In the internet, it exists essentially in 2 parts, 2 forms that are very visible to everyone, UDP and TCP. TCP is what gives the name to this family of protocols. The difference between UDP is essentially that UDP is unreliable and TCP is reliable. What does this mean? The naming is a bit weird. TCP is not necessarily always reliable. If you break a line between A and B, you've lost communication and TCP will not be able to repair it. However, TCP will do everything that is possible to repair any problem that occurs in the communication between A and B. And any kind of problems that occur between A and B is invariably translated into a loss of packets. Information is transported with packets. When packets are lost, TCP will do everything that can physically be done to repair the loss. The side effect of this is that as an application programmer, if you use TCP, you can assume that the data is delivered or nothing works. If the end system does not respond after some time, you may decide to break the connection, but there is no point trying to repair the connection because TCP has done everything that could be done for you. So of course, it simplifies a lot of the work. When you transfer a video file that is made of 2,000 packets, for example, you will not need, as an application programmer, to number the packets, make sure all the 2,000 ones have been received, because packets may be lost on the internet, are frequently lost. No, with a high probability, but in any connection that you send over the internet, it's very likely that a few packets will be lost, so they need to be repaired. UDP doesn't do that. So UDP gives you the bare bone access to the network by saying, I have some piece of information to send, I send it, and if it's lost, well, it's up to you to do something. So UDP is typically used for a number of things, but as a first approximation, we can say for very short transactions. If I send a ping to someone, for example, I send a request to a domain name server, we'll cover that in a few more minutes, then you send only one message. So there's, and you expect an answer. So if the answer doesn't come, it's the same as detecting that the packet was lost. It may be that the answer doesn't come because the server is down or but the packet is lost, but the net effect is the same. The application logic will send a request, and if nothing comes, we'll try again. So the application logic doesn't need reliability because it will automatically do things if it doesn't get an answer. So that's the difference between UDP and TCP. A second difference, which is completely orthogonal to reliability, is that UDP is message-oriented versus TCP being stream-oriented. What does this mean? Message-oriented means if I am a programmer and I use UDP to send one message, at the other end of the world, when this message is received by a UDP machine, remember the layer mechanism means if you use UDP, you must use the same UDP at the source and destination. So if the destination will receive this message, or nothing if something goes wrong, if the packet is lost, or if the message is made of several packets and is lost, then the destination will receive nothing, which means as an application programmer, when you receive something, you don't need to worry about, am I receiving half of the information? Which if you do, if you decode strings, for example, if you receive only half of the string, of course, you cannot decode it entirely. So with UDP, you don't need to do that. So the application programming interface is very simple, not reliable, but very simple. TCP, in contrast, doesn't do that because it tries to repair the losses. So if I send 2,000 packets and one is lost, TCP will not tell you exactly which packet is lost. TCP will simply refuse to deliver the data that follow the loss. TCP will insist on delivering the data in the order that they were sent. So the programming interface that you have when you read from when you receive data from TCP is the same as when you read from a binary file. You just have bytes that you read one after the other. You don't know whether the source has created 2 blocks of 10,000 bytes. This information is lost by TCP. That's a stream service. Why it is like this is historical. It's not in the nature of reliability, and we will see things that try to mitigate those here. We will also later study QUIC. QUIC is not a formal transport protocol, but it's a replacement of transport protocol, a kind of super TCP, and we'll talk more about that a bit later. One thing that we'll be exposed to is the port numbers. So as soon as we will do practical work, we'll see port numbers everywhere. So port numbers is our first example of addresses, although they are not called addresses, but port numbers. They are used to identify processes or tasks inside a machine. For example, if I have here this machine that sends a packet to that one, this is a web browser, for example, this is a DNS server. This machine is sending a request to the DNS server to resolve a name. No, and we'll talk about that in a second, what this is all about. Well, there might be multiple processes in the machine that are talking to different things. For example, you may have one name resolver, you may have multiple applications that are trying to resolve names or to do other things. So when a message, and the same thing is in the DNS server, the DNS server primary function is to respond to DNS queries, but it's a computer also, so you can log into it. So it has also other processes that give you, for example, a remote shell into the computer. So it has also other processes. So when a packet comes and is to be delivered to an application program, in order to know to which application program and to which thread or process in the application program it should be delivered, we use port numbers. So the operating system has the concept of port numbers, and when we use a UDP, you will need to say, I want to receive now all the packets that come to this machine on port 53. This is what normally a DNS server does. There is also a source port number because when the program here sends a packet, it says, I am connected to this port, which means I will receive everything that goes to this port, 1267. And also everything that I send will be labeled as source port number 1267. So that when the host, the destination host receives a DNS query, for example, it will know whom to send it back to. So when the response comes, the machine knows to whom to send it to. So very simple, but that will be visible everywhere. So the port numbers are things that belong to the transport layer and are used to identify who is the source or destination inside a given machine. Of course, the same port number can be used in multiple machines. There are lots of DNS servers in the world. Most of them are listening to are associated with port number 53. So that was the transport layer. Now we go to the interconnection layer. Right? The goal of the network layer is this thing here, is to solve this problem. We have probably 1 or more billions of devices in the world. How do we interconnect all of them together? Well, we can draw wires or wireless channels between all of them, but of course that's not efficient. So that's the goal of the network layer. The very first network layer were not like today. So the first computer network that worked, that could be used to send emails and things like this, that was in the 60s already. It used store and forward. So at that time, the computers were not many. So a computer network was made by having multiple computers that were connected by point-to-point lines over telephone lines at that time and modems. And when I would send a packet from one machine to the other, it would be first sent point-to-point to another machine. And it was called store and forward. Store and forward means that the message was entirely stored and delivered here. That was the first technology. The major invention that led to the internet was to go away from that. In this store and forward mechanism, we had essentially only 2 layers, the application layer and the physical layer. We could send a computer point to point from A to B, and then any relaying was done in the application layer. We will find some of this in the internet that exists today, but the major invention that led to the internet the way it is today was to separate this from another idea, which is to break the information into smaller pieces. At that time, that was not obvious. At that time, when the first networks were made, the information pieces were small. Essentially, we would exchange only text here. You didn't have video that you would exchange over the computer networks in the 70s. But later, the idea came to use smaller pieces of information that today we call IP packets here. So one IP packet is a piece of information, and there are multiple ways to do it, but in the internet, the idea of an IP packet is that it corresponds to a postcard. A postcard, what is specific about a postcard is that if you send a message through 20 postcards, every postcard will have all addressing information. So every IP packet contains the address of the destination, is an entity that can be delivered correctly to the destination here. Of course, it contains the source, but this will come later. So this was invented in the beginning of the 70s. And how does it work today? If you send a big mail, which normally you shouldn't, but if you do that, then your mail will be first if you send a video, for example, or a big image by mail, it will be broken into several packets between your computer and the mail server. But the path between your computer and the mail server will not be store and forward. It will not be directly a physical link between you and the mail server. It will go via those devices that are that are called routers, which are like computers, but specialized for sending packets. And then we see that this is broken into pieces and eventually will reach the destination. So here we have a mixture of store and forward at the application layer, which we find here. But here, normally, if A and B are not on different mail servers, Normally, the path is we go from a computer to a mail server, from a mail server to another one, and then to the destination. You don't go to a hierarchy of 20 mail servers, for example, like you would do for the post office. If I send a mail or a packet to the US, for example, the mail will first go to the switching center of the post office and will be delivered, store, and forward. Here, that's not what happens here. Why do you think that this change was done? What is the primary benefit of that? Okay. So while the poll is going on, there was a question, is this anonymous? So the answer is yes. The speak up is anonymous, so you can give whatever answer. It will not be used for grading you. So it's completely anonymous, except for the speak up servers. So if there are issues with the use of speak up, the anonymity can be removed by the authorities. But for me, it's completely anonymous. I close the poll. And the majority says, you should see the answer on your speak up display. The majority says A, it reduces the buffer required in routers. And this is exactly the correct answer. Let me try to get the next hidden slides. This is exactly explaining what is the benefit of packet forwarding, of packet switching versus store and forward. Incidentally, it's interesting to understand those diagrams. Those are what I call time and space diagrams. So I'm showing here time flowing vertically and space is horizontally. If I have a large message to send and I do store and forward, this is what will happen here. If I break it into packets, and if the intermediate system is able to forward the packets very fast, because it's not clogged with queuing, for example, this is what will happen. So the major difference is, of course, the storage here. In this simple case, the intermediate system needs to store one packet. One packet is 1500 bytes, as opposed to a video file of 1 gigabyte. So the storage here is much smaller. Not only the storage, but also the delay, right? So the delay is also reduced because here I pay the transmission time twice here. I'm showing here on the vertical axis two different things. If you notice, the boxes that show the transmission are slanted, which captures the fact that propagation time is non-zero here. When I transmit some data from A to B, there's propagation. We'll come back to that. And the transmission time is given by the speed of the line. Here we pay the transmission of the big object twice here. Capacity is not increased. So that doesn't improve the megabits per second or the gigabits per second of the links, but it reduces time. Time is everything in the internet. Latency is really the thing that all the internet protocols are trying very hard to improve. So the first step was this one. Here is an example of the network layer of EPFL, at least a very small subset of it. The boxes here represent routers. The lines here represent local area networks with Ethernet switches that are not shown. And I'm showing also the addresses of different machines here. Do you notice anything special? Yes?
All the machines that use EPFL submit are 128, 128.
Yes, all machines that are at EPFL start with 128, 178. So that's very typical of the way IP addresses are given. IP addresses are structured and they are the prefix, the beginning of the address typically means the organization to which they belong. So they are not random numbers. In particular, any machine in the world that has a packet to send to 128.178.71.34 can analyze that the destination prefix is this one, and this is used to simplify the routing tables in the internet. We will contrast that to MAC layer addresses that don't have this property. The addresses this is called IPv4. The IPv4 addresses are denoted in the way that is given here, not always, but almost always. A sequence of 4 words. Each word is a number between 0 and 255 that represents 8 bits. This is the way that was found in the 70s to represent 2 hex digits. If we would do it today, we would represent a number between 0 and 255 as 2 hex digits, but at that time, it was given in this form here. So every block here represents 8 bits. I mentioned IPv4 because today, the current version of the Internet protocol is IPv6. I say the current version, but most AT-EPFL is using IPv4. In fact, the wireless network of EPFL does not support IPv6, in spite me asking every year that they support it, but we were hoping to get it a few years ago, but now it's hopefully not possible anymore. So IP addresses, which identify interfaces in the world. I mentioned that an IP packet is like a postcard. So when you send a postcard, you need to give the address. In the internet, the address is the IP address. So an IP address, an IPv6 address, is made of 128 bits and is written typically with hex digits. For example, here is an EPFL public address, that's something like this. IPv4 is similar, except it's 32 bits, and we typically write them using decimal representation. So those are, as we've seen, those IP addresses here. The bad thing is that IPv4 and IPv6 are distinct and incompatible. So if I take the postcard analogy, it is as if there would be 2 postal services, one called Post 4 and the other Post 6. And if you want to send a letter to somebody who has a Post 6 address, then you have to use the Post 6 service. This is how the internet, unfortunately, is organized. I say unfortunately because it causes a lot of complexities, but it's also fortunate for network engineers because since the thing is complex, it gives job opportunities. But unfortunately, because in particular, the move from IPv4 to IPv6 is very slow. We see all the things I've mentioned before. So there is a lot of inertia in still using IPv4 because the interworking with the two is not so simple, as we will see. Of course, we will do all the labs and everything with both IPv6 and IPv4. And in fact, much of the rework of the lab we had to do this year was to make sure that you will be able to have IPv6, whatever network access you use, using a technology called Teredo that allows to have IPv6 if you have only IPv4. So many of you probably will have only IPv4 at home, or at least on the wireless network of EPFL. Many will also have IPv6, but with this technology, we make sure everything will work. So the IP layer uses addresses, but we see also very often in the internet names. So names, the very first idea of names is to be human-readable synonyms for addresses. They can be used for lots of other things, but the first approximation is this. So for example, when I see a name like this, www.newzherald.co.nz, this is a synonym for the IP address of a server, probably a web server, because it's called www.something, is the IP address of this. Why we have names? Well, first, because when the internet was invented and packet switching was started with IP addresses, it was felt that it's more convenient to use human-readable things than addresses. With IPv6, then we're very happy that names exist because IPv4 addresses are very short and can easily be memorized. IPv6 addresses are huge and you can forget memorizing them, except for very specific ones. Names are structured, unlike IP addresses, or IP addresses represent, for example, the fact that it's a CPFL, but it's very shallow structure. In contrast, names are very deeply structured, and a name is, unlike the addresses also, the structuring goes from less specific to, from more specific to less specific. So a name like this, which you probably all know, the last block of a name block is separated by dots, and the last block represent what is called the high-level domain. If it's 2 letters, it's a country. So all those things here are country names, CH, NZ, and GL. And other things represent, for example, here, anything that's commercial. And then today, any name can be possibly invented. Voila. We will continue after the break. So we will break for 15 minutes and resume live and in Zoom in 15 minutes.